All right, so I went ahead and plugged all these values into my calculator already. So I'm not going to do that again because I didn't want to waste any time. But I got a value for I2 of 56.3 milliamps. Okay, so I'm going to go ahead and box that. That is taking all of these values here and plugging them in to this expression for I2. So I get 56.3. We also know already I3, right? We know that I3 was just equal to IS, right, from the previous slide. That's right here. And so our IS value is 50 milliamps. So my I3 is going to be 50 milliamps. And so the only thing left for me to find here is I1, which again, I said that we can determine by plugging our I2 value, right, and the other values back into this expression for I1. So let's go ahead and take this and bring it on over. And I will just throw these values in my calculator now. So let me do that real quick. So I'm going to have V1, which is 3 volts, minus I2R2. So I2, again, is 56.3 milliamps. And then that's going to be multiplied by R2, which is 50, right? And then I divide that by 550, which is R1 plus R2, and I get 0.00. I don't think this is right. Hold on. Let me see what I get here. Yeah, that's right. Okay, so 0.336 milliamps is what I get there. All right, so I'm going to take this tool and box that, and now I've got my 3 currents for this circuit. Okay, so those are my I1, I2, and I3. Those are my loop currents, basically. And I want to be very careful here. I want to just kind of take a second to talk about this. I1 is the current flowing in this loop, right? That doesn't mean that that's the current flowing in R2. That's the current flowing in R1, because if I analyze this circuit, right, this loop is part of the current that contributes to R2, right? If we do KCL at this node, the loop current here is this current plus this current, and that's going to give me this current through R2. So the current that's flowing I1, the only resistor, the only component in the circuit that only sees I1 is this current, is this resistor right here, right? The only current flowing in that resistor is the current I1. The only current flowing in this resistor, right, is the current I3. But if we look at this resistor, it's got contributions due to KCL from I3, which I3 flows this way, and I2, which flows this way. So doing KCL at this node, we can determine the current that flows through R3 to be, again, I2 minus I3 is going to give me that current. So we need to keep that in mind when we go to find the voltages. So let's go ahead and just take a copy of this circuit, and remember that what we want to find is, actually, let's just take a copy of all of this. We'll copy it on over. I actually left myself another page here that we can use. Let's make this smaller. Okay. And then let's go get our current values. I only need these. Okay. And we should be able to go and solve for our voltages now that we have these currents. Let me move these over here, and then I can move these here. All right, just some reorganizing. All right, cool. So now our job now is to find these voltages, okay? So let's go ahead and do that. The first one that's trivial is the voltage Vs, right? If I just trace ground right to this voltage source here, and I know that the plus terminal of my source is connected to Vs, the minus terminal is connected to ground, then Vs has to be equal to that voltage source's voltage rating, right? Which in this case, V2 is 6 volts. So Vs is just going to be 6 volts right off the bat. So I can go ahead and box that. Okay. the rest of them aren't so trivial. I mean, R1 is pretty trivial, right? We can find R1 pretty quickly. We know that R1, if I look at this part of the circuit, right, I have a voltage drop, I have a voltage drop here. That is going to be I1 times R1. And so if I take I1 times R1, I can find the voltage VW, right? Let me analyze it using Ohm's law. Looking at the circuit right here, across R1, I can basically say that 0 minus VW, right, over R1 is going to give me I1. Okay, and we know I1, we know R1, so we can really easily find VW. So let me rearrange that, and let's say that VW is equal to I1 over R1, and that's going to be negative. So that's going to be 0.0336, 0.336 milliamps negative divided by R1, which is 500 ohms. Okay, let's see what that comes out to. Get a very, very tiny voltage there. Let me make sure that that makes sense. I actually ran the circuit in Spice, so I want to just check against my Spice sim to make sure that I get the correct value here. Open up my Spice error log. So VW, I get a very tiny voltage. Is that correct? No, it's not. I'm getting something ridiculously small. All right, gonna have to take a second. Oh, I see why. I'm ridiculous. I multiply by R1, not divide by R1. So this is going to be I1 times R1. I1 times R1, which is going to be, that makes more sense. Yeah, okay, 0.167 volts. That's exactly what I got in Spice. Okay, perfect. Negative 0.167 volts. Okay, so that's my value for VW. So now I've found VW and I've found VS, right? We need to find the rest of our voltages now. VZ, pretty trivial to find because I know VW, right? So if I know VW, I have two options here. I can start at VW and I can just go right across this voltage source, and I know that VZ has to be V1 volts higher than VW, right? V1 is only 3 volts, so I can just take this voltage and add 3 to it, and that should give me VZ. I could also look at Ohm's law across R2, right? I know I1, I know I2, I know that those are the currents flowing through this resistor. So I could use Ohm's law, and I could say I1 plus I2 times R2 is going to give me VZ as well, okay? But I'm just going to take the easy route and just add 3 volts to this value. Okay, so let me do that. And I get 2.83 volts for VZ. So basically I can say that VZ is equal to VW plus V1, which is equal to negative 0.167 volts plus 3 volts. And I get 2.83 volts for VZ. And I confirm with LT Spice, and that's correct. Okay, so let me box this. So I've got VZ, I've got VW, I've got VS. I need to find VX and VY. Again, it's pretty trivial using Ohm's law to find Vx. I know that my voltage drop across R5 is going to be Vx minus Vw, right? I divide that by R5, and that gives me the current that flows in R5, which is I3, which I know. And so I can rearrange this to get that Vx is going to be equal to I3, times R5 plus Vw, right? Which in this case is 50 milliamps times 200 ohms plus VW, which I already know is negative 0.167 volts. All right, so let's go ahead and solve for that. 10 minus 0.167, and I get 9.833. Confirm with Spice, that is correct. Vx is equal to 9.833 volts. All right, and my final, my final value here is my value for Vy, which again I can find very easily by looking at the voltage drop across R4 here, right? My voltage drop is going to be Vy minus Vx. is divided by R4 gives me I3. So I can say that Vy is equal to I3 times R4 plus Vx, which in this case is 50 milliamps times, what is R4? 400 ohms plus 9.83 volts. Let's move that. It's running out of room. All right, and so that should be 20 plus 9.83, which gives me 29.83 volts. And that's correct. That is correct according to LT Spice. All right, so we have now solved for all the currents and all the voltages in this circuit. We've got Vs, Vw, Vz, Vx, and Vy, and we've got I1, I2, and I3. Solve using mesh analysis. Definitely painful. The algebra is tedious, and I made a lot of mistakes along the way that I corrected. And it's easy to make mistakes. These mesh analysis problems are tricky. You have to be very meticulous when you go through the algebra. But that's it, guys. That wraps up Module 3. That wraps up this example problem, and I'm going to go ahead and end this video here. I'm super excited that we've made it through the DC analysis portion of this course. And yeah, we'll see you guys in Module 4.